the last semester before I did it, plus it. But it wasn't the rest of my life. Because I've got so, like, I had a friend. It's like studying stuff. And everything. Whether I mean, yes, I ranked through
Okay. So here's one. They don't all have to be funny, right?
Yeah, what do you have there? Yeah. And he's so happy. Is he sitting? Where's he sitting? On your lap. Did he give you a kiss? Did he give you a kiss? Do you love Baba? Yeah. Sweet buddy.
You should have kids someday.
Samuel, what do you have there?
The moments like these outweigh, getting up at 3 in the morning every other night and all these things. Okay. All right. Okay. So first we have to, let's do this one. We need a good sketch. So we need to recognize that that is a circle, center, 0, 6, radius 2. So this is radius 2. I'll call it capital R. Center is 0, 6. And we're going to rotate this about the x-axis. So what do you get when you rotate that about the x-axis? Right, what is that? That's probably my worst picture ever. This is kind of hard to draw, actually, because everything's curved. There's no straight lines in it. Done. And the cross sections are circular. Right, so that's just a donut, right? This is a donut, so the cross sections are circular. Okay, and so if we're going to use shells to do this, are we going to take vertical strips or horizontal strips that will produce shells? Horizontal strips will produce shells. Okay, and so then we're going to imagine our shell then looks like this. Like that. So that's the shell we're going to get. Where this is what the circle is like up here, right? And that circle is going to go around this way. Okay, and so our volume of our shell is 2 pi r times height times thickness or width. So what's the radius of this thing? So the radius is from here to here. So that's the radius. X, Y, change in X or change in Y? From we're rotating about the x-axis, so that distance up to the strip, just Y, just Y. That's the Y coordinate. So we got 2 pi Y. What's H? H is then this dimension here, do it in blue. That's H of our shell, so it's H here. X, Y, change in X or change in Y? That's a change in x, but by symmetry, we can kind of make that easier than that. So yeah, so we could say that's a change in x, or we could look at the symmetry and just say that that is 2x. Because we're going the same distance to the left as to the right of the x-axis, so that whole thing is 2x. So we get 2 pi y, 2x. Width is delta x or delta y? Delta y, so we got to write this x in terms of y. This y is fine. We can just leave it. So that's where this comes in, the equation. So we need to solve x in terms of y. So x squared equals 4 minus y minus 6 squared. And x equals plus or minus the square root of 4 minus y minus 6 squared. And is that equal to 2 minus y minus 6? You guys say square root of 4, square root of y minus 6 squared? No, watch out. I watch students do this all the time. If you have a square root of a sum or a difference, you can't take the square root of the terms. You can't break that up, okay? If you had a product in here, or a quotient, great, put a square root on all the factors. But if you have a sum or a difference, you're locked into this, okay? Because if that were true, then look, what would the Pythagorean theorem end up being? What would the Pythagorean theorem end up being? C equals A plus B. And certainly, I hope you know that it cannot possibly be right? Or else it would not be c squared plus a squared plus b squared. It'd be c equals a plus b. But that's what you're doing. If you're saying the square root of a sum is the sum of the square roots, then you're saying the Pythagorean theorem could have been written a lot simpler as c equals a plus b. No. Okay? So same thing here. Okay. And so what do we got? So we got our x in terms of y. And we're going to use the plus side because we can just say this x is going to be the plus version of that square root and then times 2. So we're ready to write out the whole thing. 2 pi y times 2 times square root of 4 minus y minus 6 squared delta y. So there's our typical element. Volume of the typical element, in this case a shell. 2 pi y, 2 times radical 4 minus y minus 6 squared delta y. Okay, where do we go from here? So we set up the integral. What's that?
Does it not matter that one is like that there's a positive and negative radical?
But so that was taken care of by the fact that we know this dimension is 2x.
Oh.
So yeah, you could do the positive and the negative and do the change in x, and then you'd have the positive minus the negative, and you get 2 times.
Oh, okay.
You see, it works out the same way. Yeah. But the 2x saves a lot of writing, right? Okay, so then we're going to integrate y goes from, you got to figure out what that y value is, to that y value. So if the rate, so if we're at center of y equals 6, the radius is 2, it'll go from 4 to 8. So we'll go from 4 to 8. So I'll just do 4 pi y. 2 times 2. Square root of 4 minus y minus 6 squared. And so then the question is, do we still have a active and functional toolbox of techniques for solving integrals? Do we recognize what this will be, how we will do this? Remember all the different tools we learned, and can you recognize which one applies here? Yeah, we want to start with a change of variables. Yep, so start with a change of variables. Use substitution. So say u equals y minus 6. Then du equals dy. That's easy. Y equals u plus 6. We can rewrite this then as integral 4 pi times u plus 6 square root of 4 minus u squared du. Now we've got 2 integrals, right? We've got this sum, right? So we're going to do everything times u, and then everything times 6. So when we do everything times u, how will we do that? antiderivative. We take u times 4 pi and times that radical. It undoes the chain rule, right? Undoing the chain rule. And then we'll have 6 times 4 pi and 6 times that. So this equals integral 4 pi u square root du plus integral 4 pi times 6 square root du. And how do we do that? 4 pi 6 times radical 4 minus u squared du. Remember how to do that? It's this right here, the square root of a squared minus u squared. What's that? Table, right? Table. So we're looking for a general form of square root of a constant squared minus the variable squared. And that's a table formula. So that's undoing the chain rule, table formula, and we got it. Questions on this? Much more interested in this getting the setup right, okay? The setup is the most important thing here. But hopefully we've learned and retained how we would do this, and we have all the tools to do this if you just remember. Yeah?
It's kind of a general question. We had talked about last class, if you want to solve the integral and you pull out the pi, you can still do that, but you said it's not technically a volume.
No, then what's left inside the integral is not a volume of one element.
Right, but is that still okay to do that on the test just to like solve it?
Yeah, sure.
Okay.
Yeah, I mean, we're trying to get the number, yeah, it's fine. It's just the disadvantage to factoring that out is now what you're looking at inside the integral is no longer the volume of your element. But the whole thing still equals the volume of the solid. Yep.
Professor?
Yeah.
Is it because the pi allows it to be able to allows you to be able to integrate it by y? Is that's
The
kind
pi?
of like a conversion factor?
The pi?
The 2 pi.
No, it goes back to that we've built the volume of one element, right? So we followed the formula for the volume of one element, right? And that's that. That's the whole point. That formula right there, that expression, is the volume of one thing that we're going to add a bunch of those up together. If you take away the 2 pi, then it's no longer a volume. That's all there is to it. It's not about. I'm not sure what you were trying to relate it to y. It's just the fact that the whole premise of this integral is that we find the volume of one element, and then we add up a bunch of those, right? So if you factor out any of these values, it's no longer the volume of that one element. Does that answer your question? Okay. Other questions on homework? Okay, so we got a little bit more volume stuff to do. So let's look at a new way of generating a potential. No, let's do this first. So let's look at how this integration technique of revolution of pancake revolving a region to get solid and then find the solid. You can use it to derive the common geometry formulas. So let's do that. Let's derive the volume of a sphere. So if we wanted to derive the volume of a sphere using what we're learning here about volumes of revolution and washers and pancakes and shells, how would we start? What would we do? We want to derive the volume of the sphere. We've got everything we need. We just got to set the frame of the situation correctly, and then apply what we've learned. So how would we start that? What do we do? Yeah.
You have like an orange slice kind of being rotated around an axis.
When you say an orange slice, what do you mean?
Like a wedge.
3-dimensional or 2-dimensional?
2-dimensional.
Okay, so like a half disk?
Yeah.
Yeah, so we always started with a region, right? We always started with a region. So we've got to, if we're going to do a solid revolution, we got to have a region. So what region do we want? So he's saying do the top half of a circle. So let's take a circle, and we'll make this region right here. Now, we want it to be any circle. So how do I, so if I'm writing any circle, what would that be if it represents any circle? Somebody new. Put it on the origin, make it easy for yourself. Put the center on the origin.
X squared plus y squared equals r squared.
Yeah. So we'll call it capital R because we know we use little r for stuff in our elements. All right, and so now we want to form this volume of a sphere out of this region. What are we going to do? We want a solid that's a sphere. What's that? No, we want it to be any circle. So our goal is to get the volume for a sphere for any radius. She wants to rotate around the x-axis. Yeah, rotate that around the x-axis and you'll get a sphere, right? So we're going to rotate about x-axis. Okay, and then we know we'll have that sphere. So if we use, so we could use horizontal or vertical strips, and we should know what elements we would have. And if we use vertical strips, we would know what elements we would have. We should. So that would be a potential test question. If I use vertical strips here, what kind of elements would I have? Two people are saying pancakes. Agree with that? And if I had horizontal strips, that would make our shells. So, choice is clear. What should we do? Pancakes are the easiest, right? Volume of a pancake is cylinder. Now, this radius, now we're talking about the radius of our shell, not capital R, or the radius of our pancake. So we're reserving big R to be this fixed parameter, this fixed value of the radius of the sphere. Little r can change based on the pancake, right? It's the radius of a pancake. So 4 pi r squared, pi r squared h. What is r? Oh, so I should have drawn it here. So we're talking about finding what? Volume of a typical pancake. So yeah, x, y. So hopefully you got in the habit of asking this question to yourself whenever you're finding a radius or a height or any distance in these elements. Is it x, y, change in x, or change in y? It's just y, right? So pi y squared. And then h is? Yeah, I should have said width or whatever. So it's just the width of it, so delta x. Not really height, right? Width. Height of the pancake on its side. Yeah, that's right. Okay, so we got delta x, so we got to write y in terms of x. But actually, look, we got y squared. That makes it even easier. What is y squared? So just, instead of solving for y and plugging it in, let's just solve for y squared. What's y squared? Yeah? Make things easier on yourself. Okay, so that's the volume of our pancake. Now that's a capital R, right? That's a capital R. And then what are we going to do? We're going to integrate those to get the volume of the sphere. We're going to integrate from x equals. Yeah, so we could do negative capital R to positive capital R, or we could do what? 2 times 0 to R. Let's use that symmetry, get a 0 in there. And then we'll have pi r squared minus x squared dx. And what are we expecting? When all is said and done, we should get? Do you remember what the volume of a sphere is? Yeah, she got it. 4/3 pi capital R cubed. So when we do that, that's what we should get, right? So let's see it work. Ready? So 2 times pi r squared x minus 2 pi x cubed over 3 from 0 to r. Are you following? We're integrating with respect to x. Capital R is just a constant. right? Capital R is just a constant. Good so far? Equals. So we're going to plug capital R in, and when we plug 0 in, it all goes away, right? This is just 0 and 0, so that was a good choice to use the symmetry. So we just got to plug R in here, so we get 2 pi R squared times R minus 2 pi R cubed over 3. So this is 2/3 R cubed. What is this? 6/3. So we got 6/3 pi R cubed minus 2/3. It's feeling good. Got it. Oh, technicalities. All right, I got it. Pretty cool, huh? So we just derived, using these solids of revolution, just derived the volume of a sphere, the same formula that you've known from high school geometry. And what did we need to do that? Well, all these problems started with our region, right? So we had to pick the right region and rotate it about the right thing. So we had to decide that this time, right? We had to come up with that so that it matched our goal, right? Our goal of volume of a sphere. Okay, so you'll be deriving the volume of a cone. And you got to think through all the steps. Volume of a cone is 1/3 pi R squared H. Now that R, that's the radius of the base of the cone. That's right? So this is R. If you go anywhere from the base, that is a smaller radius. But capital R in the formula is the radius of the base only. Okay? And then that's the height. So that's a very attainable exercise. You can do that. That's a good exercise. So you're going to prove that the volume of a cone using our techniques of integration here. Prove that the volume is 1/3 pi R squared H. And I'll write that again on Blackboard in the assignments area. Okay, any questions?
We're not doing that right now.
No, yes, for homework. Everyone will do it individually for homework. Yeah, no, that's not an in-class activity. Sorry, I didn't clarify that. Yeah, you'll do that homework. Okay, questions on the sphere example? Okay, so then there's another way to generate solids, not by revolution, but by stacking shapes. So let's do just one of those. Don't want to spend a long time on it. But we can also generate solids by stacking shapes of a different, or stacking stuff instead of rotating. Can I erase the screen that's up now? Okay, so for instance, oh, look at that, beautiful. Okay, so for instance, say I have the region bounded by y equals sine x, y equals 0 in the first quadrant. And cross sections parallel to the y-axis are, should make it right triangles. No. Let's do something. Let's do rectangles. Whose height is 3 times the base. All right, so we gotta imagine this. So we're not rotating anymore. So we're starting with a region. So start this. The region is y equals sine x formed by y equals sine x, y equals 0 in the first quadrant. That should be easy sketch. Okay. Sorry, so that, and then be x from 0 to pi. Okay, so x from 0 to pi, because in the first quadrant there's other places. We just want this first part of sine there. So here's our region. And what are we going to do? We're going to stack, so that's going to be the base of our solid. That'll be the bottom of it. And then stacked up on top of that, like coming out of the screen towards you, will be every cross-section parallel to the y-axis. So if I start with, that's going to be a vertical strip. So you're going to have like a rectangle that's 3 times taller this way than that dimension that I just showed you. Okay, so you're going to have coming right out at you, standing up on end on that thing, is a rectangle 3 times taller it's not my sketching day today. Here. Okay, I think that's a little better. Okay, so they're all going to be standing up on end. So let's see if I can draw this actually. So here's the base of this. So this is like the floor. Okay, so that's now looking. This is that initial region, and then all the cross sections are going to be rectangles that are 3 times taller than the base dimension. Okay, so there's that one. There's this one way up like this. Does it make sense? And then the shorter one over here. See what it's like? So what we'll get is, so the very tallest one will be right in the middle because that's the biggest base. Okay, and so then they'll all pretty good, except something like that. Okay, so if you sliced it, you'd always get if you sliced it in and out of the screen, you'd always get a rectangle. And that rectangle is 3 times as tall as it is at the base. Okay? So you get little short ones here on the ends, and then in the middle you get the tallest one, where y is maximum there, you get the tallest one. Can you kind of see it? So it's kind of like this weird wedge thing. So we don't get it by rotating, we get it by stacking rectangles that have all different shapes, but their height is always 3 times as their base across that thing. Okay, so this is not hard. I mean, so maybe drawing it and drawing it's a little challenging, but this isn't hard because all we have to do is just do the volume of a typical rectangle, which is easy. So what is the volume of this rectangular wafer here? So it's just, I can't draw anything today. Okay, so that's it. So it's just what? Length times width times height. So let's do the, we'll call this the height. What is the height? It's just a y-coordinate, right? It's just the y-coordinate of the graph, right? So h is just y. What's the width? So that's this little dimension here. Delta x, piece of cake. And then what's the length? So what's this dimension? 3 times height, 3 times the height, which we know is 3y. So now we just got to write y in terms of, so we got what? 3y squared delta x, but we need to write in terms of x, so it's going to be 3 what? Sine squared x, delta x. So that's the volume of one of these like rectangular wafer things, rectangular planks. That's going to be standing up on the top of this region that's the base. Okay, so then the volume of the solid, that thing, equals, so now we have delta x, so we're going to integrate from 0 to pi. That's where sine comes back and crosses the x-axis of 3 sine squared x dx. And we all remember how to integrate sine squared? I heard one person say it, but you're all thinking it, right? Half angle formula. Home free, right? Easy. But that you got to remember that. To integrate sine squared or cosine squared, that's the half angle identity. Half angle identity. So then that will be the volume of this thing that if you sliced it, you always sliced it up and down like this, you'd always get a rectangle. And its base is like this region formed by the sine curve. Does the premise make sense? So you just have to understand the premise, then the math is even easier than these rotation, right? So once you kind of understand the situation, then usually these elements now are easier than the rotation elements. Okay, they're like squares or rectangles or triangles or semicircular discs or something like that. Does it make sense? Any questions on that? So you got some web work, some practice of that stuff. Last chance. Question. Okay, so then let's move on from volume then. We're done with volume. So let's see if I can find the PowerPoint. Okay, so remember this. Rate quantity perspective, right? So what happens? If we sum up small changes in a quantity, dy's, right, little dy's, we get total change in that quantity. Sum of a bunch of dy's is a total change in y. For area, right, if we sum up a bunch of areas of thin strips, we're going to get the total area of the region that those thin strips made up, right? That those thin strips made up. Volume? Volumes of elements. We're going to get thin elements of volume, right? We're going to sum up thin elements of volume. It's going to give us the total volume of a solid. So now the question is, I want to get arc length of just any function. So what will I do? What will I sum up? So not circular arc, any arc, right? A parabola, a cubic, an exponential function. I want to be able to find the length of the arc. So it's going to be about finding a little bit of something and summing it all up to get the total arc length. So what will that little bit of something be?
Would be the differences between rates of change?
No, you're kind of missing the pattern here, right? So if I want the total volume of solid, I want thin elements of volume. If I want total area of a region, thin strips of area. Total change in a quantity, little bit of changes. So if I want to get the total arc length, little what? Okay, so you might think it's little arcs, but little lengths for sure, right? Little lengths of something. So let's take a look at that. So let's draw that. The problem with little arc lengths is we don't have a formula for little arc length, right? I guess we could do circular arc, but that's kind of more complicated than it needs to be. Okay, so if we have some function here, what's that? But we're not getting a total rate, right? So adding up.
Do we add little constant like
Right.
slope, like a constant?
Exactly, right. So we're going to add little, I thought you said rates. Okay, so yeah, so what we're going to do is we're going to say this is A to B, and say, so we want to find that arc length from A to B. So from there to there. So what would be the easiest possible way? We're going to break this up and do it a little bit at a time. So what would be the easiest thing in terms of each little piece? I don't know how to draw this. Looks like it. Right, so we want to make it as easy as we can on ourselves. What I'm trying to do is make it so that you can see the lines, right? So that it's hard to do that. Okay, so right. So what we're going to do is we're going to split this up into intervals, and then rather than find a little arc length, we'll just find what? A little straight line length, like that. And then, likewise like that. These are all supposed to be the same. It's just very hard to do. I don't know how I gotta learn how to draw a curve so that you can actually see the arc lengths when you have the straight line lengths. Okay. All right, so we're going to call the whole length of the arc S. So S is the length of F. Say, this is F. From x equals A to x equals B. So how are we going to do that? We're going to sum up. So then each one of these is a little bit of, so let's say ds1, ds2, delta m to delta. So the delta s's are then little estimations of arc length, and we're going to estimate them by straight line segment to make this as easy as possible on ourselves. Because we know we take lots and lots of those, lots and lots of little segments, that will eventually become indistinguishable from the curve, right? If we took lots and lots of little line segments, that will do the trick. We don't need to make each one of these a little arc length. It's complicated and it's unnecessary because when these get really short and close together, it'll become indistinguishable from the actual curve. Okay, so the question is, so a delta, so what's our strategy then? Is that the approximate arc length will be the sum from, say, I equals 1 to the number of, so n would be the number of these, and we're going to sum up these delta SIs. So that's each one of those is a length of a little segment. And we're just going to sum up all the lengths of the little segments, right? A delta SI, so there's delta S1, It's the length of it. Then delta S2, then delta S3, etc. And there's going to be n of those. The last one will be delta Sn, and we'll just add them all up. Okay, so the question is now, how do we get a little length of segment? How do I get that little bit of length right there?
Rise over run, and then would you use Pythagorean theorem to find?
Okay, so rise over run is slope. Pythagorean theorem would give you,
So that's,
which one do you want?
isn't that essentially just like a squared plus b squared equals c squared?
Right.
There?
Yeah, so we don't want rise over run, but yes, we do want the Pythagorean theorem, which is a relationship of lengths, right? So what for this one, then what is that right there? So that length right there, if this is delta S1, then for delta S1, what would we call that? Delta X1. And this would be delta Y1. And we have a relationship between delta X1, delta Y1, and delta S1, or delta Xi. So any of those triangles that you get from starting with a line segment delta S, delta Si, so any of these would be equal to what? In terms of X and Y. Someone started to say it. So what would that length be? Square root of? Right. Square root of delta Xi squared plus delta Yi. Just going to make it. And the square root of delta x squared plus delta y squared equals delta x plus delta y, right? No. My students throughout the ages have tried to do that. All the time. I see this in the work all the time. The sum of the square root of a sum is not the sum of the square roots. The square root of a sum is not the sum of the square roots. You got to leave it like that. Okay, but so here's what we're going to do. So I'll move that over here now. So that's going to equal to. So here's what we're going to do. We know we're moving towards integral, and with integral, we have this part of the integrand that's what? Dx, or delta x. So I want to make sure, so I'm gonna get that by doing this. Watch. If I multiply by delta xi, thinking down the road, then I'm going to have some function times dx, right? Times dx. So I'm going to do that, but now I want to keep this the same. So if I multiply by delta xi, I'm going to also. Oh, I didn't think that was that hard of a question. Yeah. Divide by delta xi. Now, didn't I keep that thing the same value?
Multiply by 1.
Yeah, so I just multiply by 1, right? So I multiply by delta xi and divided by delta xi. Well, now I want to get this inside, right? So how do I get delta xi inside the square root? It will go inside the square root as it's squared, right? It'll be, so I'm going to move that in as delta xi squared. And then what I'll get is delta xi squared over delta xi squared plus delta xi squared, sorry, delta y I squared divided by delta xi squared. And that whole thing times delta xi. All right, well that's nice. What's that? Right there, delta xi squared over delta xi squared. That's just 1. And then I'm going to change this to delta yi over delta xi quantity squared. That should have a familiar feel to it right there. And then times delta xi. And so now I'm ready to say let's do a lot of these intervals that are really, really small. So I'm going to do a lot of these intervals that are really, really small, and then it's going to be the sum of all those little lengths. So now I've still preserved, I just changed the form of it. This whole thing right here, put a blue. What is the meaning of that right there? What does that calculate right there? What I put a blue circle around. One hypotenuse, right? One delta S. One hypotenuse. It's the length of one of those. So, and it approximates a little bit of arc length, right? That one hypotenuse length is still that, because that's what we started with, right? Delta SI. Okay, now as we let the delta x's get really small and we get lots and lots of intervals, this sum turns into what? So what? Greek S to German S for sum, right? Greek S for sum, German S for sum. From A to B of what? The square root of? Okay? So delta yi over delta xi when things get really small. dy dx, which is, what is that? That's the derivative of f, right? That's the derivative of f. So dy dx, derivative of f. When things get small, that's what we get. Times dx equals s. So what inside this integral here equals is equivalent to a little bit of arc length? What inside this integral here is equivalent to a little bit of arc length? What's that?
What's under the radical?
The radical. The radical is a little bit of arc length. And then this just tells you we're differentiating with respect to x. No, this is multiplication. This is part of the math. What represents a little bit of arc length here? The whole thing is ds. Not just a part. The dx, all semester, and I keep saying this, it's part of the math. It's part of the math, right? This thing under the radical just by itself is not equal to a little bit of arc length. It's times dx that gives you, what, a little bit of arc length, ds. So, from here, it's just applying this formula. Okay, you're given a function. This is s for length of arc. Okay? You're given a function, and you're given where you're going to start and where you're going to end, right? And so what do you need? You need the derivative of that function. This will be probably a function of x, maybe. Yeah. So this is the derivative of that function that you're finding the arc length for, f prime of x. You can set up this integral, a to b, and then you're off to the races applying a technique of integration to do the antiderivative. So I had an easy example, but it's just that, an easy example. You could do it, right? So it's just a matter. So now it's just doing, what lots of you are good at already, and it's just applying the formula. So given a function f and bounds a to b, you just find the derivative and then integrate from your lower x to your upper x. But this proof is important, okay? So this proof, you're responsible for this proof. It's because it's very attainable. We should understand that fully. That's not a hard proof at all. Or derivation. So for the exam 2 coming up, a couple weeks, which is the Friday after fall break, right? So we have a full week. We come back from break and have a Wednesday, and then we have the test, okay? On that test, test 2, this derivation, understanding everything that's going on here, plus using the formula is all fair game for the exam. Okay, so the next web work is due Wednesday. I'll probably add another web work on Monday, so get started on the web work over the weekend. You can fully finish the web work now with what we have, unless you need support on Monday or Tuesday. Then I'll add another web work, and then you also have the written assignment of deriving the volume of a cone. Okay? Have a good weekend.
If anyone's interested.